Good afternoon to all of you. Is my voice audible? Can you hear me?
Yes, sir.
Okay. So in the yesterday's class, we have discussed about the shapes of s orbital, and then we have moved towards the p orbital. So I told that in case of s orbital, we are having spherical shape, right? S orbitals have spherical shape. And then I told you that in case of p orbitals, they have double dumbbell shape. So double dumbbell shape means that we will have then I also told you that in case of S and P orbitals, we have nodes, and we can have a radial node or the spherical node, and we can also have the angular or the nodal plan, angular node, or what we also call it as angular node or the nodal plan. So let's move ahead, and then we will see the shapes of d orbitals. So that means p orbitals, they have dumbbell shape, and s orbitals have spherical shape. So let me share the whiteboard. So I hope that this is visible. Is it visible to all of you?
Yes.
So let's see the shapes of d orbitals. Shapes of d orbitals. So in case of d orbitals have double dumbbell shape. So that is just, I will write it here, that d orbitals have double dumbbell shape. Double dumbbell shape. So as in case of p orbitals, there was dumbbell shape, but in case of d orbitals, they have double dumbbell shape. So double dumbbell here means that we will have four lobes. In case of p orbital, we were having only two lobes, but here in case of d orbitals, we will have four lobes. So there will be four lobes. For example, we know that we are having orbitals, 5D orbitals. One is your dxy. So what will be the shape of dxy? It is just like this. For example, if we are, let's say this is your x-axis, and let's say this is your y-axis. The electrons, they are in the lobes which are in between these axes. So one lobe is just like this, another is lobe is like this. So there are, in total, there are four lobes in which electrons are present, and this we what we call as d orbital. So here will be the electrons in these four lobes. So this shape is known as double dumbbell shape. So d orbitals have double dumbbell shape. So in case of dxy, the shape will be like this. That is the four lobes, they will be in between these x and y axes. Similarly, if we just see the next one, let's say we are having dyz. So dyz, it will also have double dumbbell shape, but here the axis will be different. Axis will be different. For example, let's say this is your y axis, and this time let's say this is your z axis. So if we are having y and z axes, and the lobes are in between these, then we call it as dyz orbital. Are you getting? So electrons will be here in these lobes. Is it clear? Simply you have to remember, in case of d orbitals, there is double dumbbell shape. That means there will be four lobes, and these lobes in case of dxy, these are in between the x and y axes. And in case of dyz, the lobes are in between y and z axis. Then we are having next is your dzx orbital. In case of dzx, so we are also here having the two axes. So one will be your x-axis, another will be your z-axis. So let's say this is your x-axis, and let's say this one is your z-axis. Now tell me, in case of this dzx, the lobes will be in between these two axes, that is your x and z axis, just like this. So in this region, you will just find the electrons here in case of d zx. So this is also your double dumbbell shape because it also has the four lobes. So in case of these three, that is dxy, dyz, and dzx, you have to remember that the lobes of these, they are in between the axes. But now if we just talk of another one orbital, that's your dx square dash y square, dx square dash y square. In case of dx square dash y square, you will see that the lobes or the electrons are on the axis. For example, let's say this is your x-axis. Let's say this is your y-axis. Now here, the electrons, they will not be in between the axes. They will just be on the axis, just like this. So electrons will be here, the lobes will be here on the axis, just like this. So this is your dx square dash y square. Then we are having the dz square. So this is the last d orbital. We are having 5d orbitals. So dz square, it has also double dumbbell shape, but here you have to remember, let's say this is your here x-axis and this one is your z-axis. The lobe is on the axis, just like this. This is one of the lobe and this is another lobe. Along with that, electrons are also in the circular motion like this. So this is known as, this shape is your dz square and it is known as donut shape. So dz square, it has donut shape. It has donut shape. So you have to remember this, that dz square, it has donut shape. And all these shapes, that is your dx, y, dy, z, d, just we are having dx square dash y square. This shape actually it resembles with clover leaf. So that's why it's also known as that they have clover leaf structure. Clover leaf structure. So they have just clover leaf structure. Clover, it is just one of the spice, isn't it? So the leaf of clover plant, it is just having this type of leaf. So that's why we say that it has clover leaf structure. And dz square, this is different shape and then the rest of these. So this is known as donut shape. And here, in case of dz square and dx square dash y square, you have to remember that the electrons, that the loops, they are not in between the axes, they are just on the axis. This is very important. You can see here that they are actually on here x and y axis, here on the z axis, right? In case of dz square, you have to remember that electrons, they lie on the z axis, and along with that, electrons also revolve around this z axis. So is it now clear? The shapes of d orbitals. So d orbitals have double dumbbell shape, and this dz square, it has donut shape, and all others have clover leaf structure. It is just like the leaf of a clover. So clover plant, clover leaf. So have you noted down this? Shall I move to the next page?
Yes, sir.
Have you noted down this?
Yes, sir.
Okay. So next, we will see here the number of nodes. That's very important. I hope you remember the formulas to calculate the number of nodes. We are having radial or spherical node, and similarly, we are having angular or nodal plan. So if you have to tell the number of spherical or radial nodes, so what is the formula? I hope you remember spherical or radial nodes. Radial nodes. So the formula is, it is n minus L minus 1, right? So can you tell me, for example, if I just say you that I'm having 3dxy, and you have to tell me the number of radial nodes or the number of spherical nodes. So can you tell me how many will be the number of radial nodes here? Can you calculate number of radial nodes? So it will be your n is here 3, n is given here 3, you can check it out, n is here 3. And what is the L value? For D, L value is 2. So that means you will write 3 minus 2 minus 1. So 3 minus 2, that's 1. 1 minus 1, that is 0. Got it? So therefore, there isn't any radial node or spherical node in case of 3dxy. In case of 3dxy, isn't any there isn't any radial or spherical node. But now if you have to tell the angular nodes, or what we call them as angular nodes, are also known as nodal plan. So can you tell me how many nodal plans will be in this 3dxy? So that is given by the formula L. So in case of this 3dxy, what is the L value? L value is 2. For D, L value is 2. I hope you remember that table. I have told you that to remember that box. I told that for S, L value is 0. For P, L value is 1. For D, L value is 2. So it means that it has two angular nodes. It has two angular nodes. So can you tell me where are these two angular nodes? For example, if I just show the d orbital is like this. We're having the 4 lobes in total. Let's say these are the 2 lobes, and then we're again having the 2 lobes here. So this is the shape of d orbital. Let's say this is your 3dxy. Now, I told you that there are actually 2 nodal plans. So you can check it out. One nodal plan, it is just like this. So in nodal plan, there isn't any electron, right? The probability of finding an electron, that is 0 in case of nodal plan, right? So this is one of the nodal plan which I have shown it here by this green shade. And similarly, the next nodal plan you can see that is just here. This is the next one. So there are 2 nodal plans in case of d orbital, that is 3dx here. Now, if I just tell you that you have to tell me the total number of nodes. So how to calculate the total number of nodes? I hope you remember the formula, how to calculate the total number of nodes. Total number of nodes, that is calculated by the formula n minus 1. So what is n value? N is here 3. So 3 minus 1, so that's 2. That's equal to 2. That's equal to 2. So then if I will just give you another example that you have to tell in, for example, if there is 6dz square, you have to tell me the spherical nodes, the nodal plans, and the total number of nodes. So can you calculate and let me know? I hope you can calculate. So in case of 6dz square, how to
3,
calculate
3, 2, and 5.
3, 2, and 5. Okay, let's see. So if I just talk of radial nodes is given by n minus L minus 1, that's 6 minus 2 minus 1. So 6 minus 2, that's 4, 4 minus 1, that's 3. So there are total 3 radial nodes. Now, if I just talk of angular nodes, angular node is given by L. So L value is 2. So that means there are 2 angular nodes. And if I just talk of total number of nodes is given by the formula n minus 1, that is 6 minus 1, that's 5. And you can clearly see here that we are having radial nodes 3 and we are having angular nodes 2. So 3 plus 2, that's 5. So total nodes will be 5. Got it? Any doubt here?
No, sir.
Okay, so shall I move to the next page? Have you noted down this?
Yes, sir. Yes.
Okay, so next is, then you have to remember that f orbitals have complex shape of f orbitals. So f orbitals have complex shape. F orbitals have complex shape. So f orbitals have complex shape that cannot be actually drawn here in this 2D board, but you should be able to calculate the number of nodes. That's very important. For example, if I will just say that I am having 4fx cube, so you have to tell me total number of nodes. So what will be the total number of nodes? It will be n minus 1, that is 4 minus 1, so that's 3, correct? And if I have to tell you the radial nodes, so radial node is given by n minus l minus 1, so n is 4, l is 3 minus 1, so that is 4 minus 3, that is 1, 1 minus 1, that is 0. And if I just talk of angular nodes, angular node will be given by the formula L. So what is L value? L value for F is 3. So there are total 3 nodes, and these 3 are actually your angular nodes. Got it? I hope you can calculate, right? So can you calculate here that if I'm just giving you 5f x y z, this is one of the f orbital, and you have to tell me the total nodes, the radial nodes, and the angular nodes. So just calculate and tell me.
1, 3, and 4.
Yes.
1, 3, and 4.
See, total nodes will be 5 minus 1, n minus 1. So 5 minus 1, that is 4. Total nodes will be 4.
So I'm telling in the
And
reverse order. So I'm telling
okay,
radial
no
nodes.
problem.
Radial nodes is
Yeah,
1, angular nodes is 3, and
yeah. Radial
4.
node will be n minus l minus 1. So that is 5 minus 3 minus 1. So 5 minus 3, that is 2. 2 minus 1, that's 1. And then the angular node will be L value is 3. So that is 3, 1, and 4. Or you can say 4, 1, 3. So I hope that you have got this, that you can easily calculate the number of nodes, that is radial, the angular nodes, the total number of nodes, right? Any doubt here? So shall I move to the next page?
Yes, sir.
Okay, then we had study. So this was the shapes of orbitals, different types of orbitals. Then we have to study how to give the electronic configuration. But before that, you had actually remember the order of energy of orbitals. So, okay, I will write it here. Energy of orbitals. Energy of orbitals. Energy of orbitals. First, let's talk of hydrogen and hydrogen-like species. For hydrogen and hydrogen-like species. What are hydrogen-like species? They are actually those species which contain hydrogen-like, are actually those which contain only one electron. Just if you are having hydrogen, we are having He positive, we are having Li2 positive, right? Let's say we are having Be3 positive. So they contain all one electron, so that means they are your hydrogen-like. They have only one electron. So for these, you have to remember that for hydrogen and hydrogen-like species, the value of energy depends only on the value of N. I will write it here. The value of energy depends only on the value of N. N is the principal quantum number, right? For example, if I will just write 1s orbital I'm having, and let's see, then I'm having the 2p orbital. Okay, let me first write the 2s and then 2p. So if I'm writing 1s, 2s, then I'm having the 2p, then let's say 3s, 3p, 3d. Similarly, let's say I'm having 4s, 4p, 4d, 4f. So here you have to remember that greater the value of n or more the value of n, more will be the energy. Higher the value of n, higher will be the energy. So that means 1s, it will have very low energy because n value here it is 1, that's very small. So its energy is least. Then 2s will have higher energy than 1s, but 2s and 2p, they will have same energy because n value is same. N value is same, 2 here, 2 here, so they have same energy. Then it is 3s. 3s will have higher energy than 2p. So 3s, 3p, and 3d, all three have equal energy. And then we're having 4s. 4s, its energy will be greater than 3d. But 4s, 4p, 4d, and 4f all will have equal energy. They have same energy. Got it? It's very important. So they have same energy. But this is only in case of hydrogen and hydrogen-like species. For other elements, I will tell you next how to tell the energy. But first here you have to remember that for hydrogen and hydrogen-like species, the order of energy will be like this. That means 1s, it will have very small energy. Then it will be your 2s and 2p. They will have equal energy. And then it will be 3s, 3p, 3d. These three will have same energy. So then it is 4s. 4s will have higher energy than 3d. Then it is 4p, 4d, and 4f. Right? Is it now clear? Have you got it? Next, you
Yes.
had to
Yes.
remember, yeah, next you had to remember for multi-electron atoms, that is other than hydrogen. So I will write here that for multi-electron atoms, for multi-electron atoms, you had to remember that the value of energy, it depends on n as well as l value. So here energy depends on both n and l value. So energy depends on both these values, n and l value. This is very important. You have to remember this. So energy in case of multi-electron atoms, that means which have electrons 2 or more than 2. So that means all those elements which are after hydrogen, they are your multi-electron atoms. Helium has 2 electrons, right? Lithium has 3 electrons. Beryllium has 4 electrons. So they are just your multi-electron atoms. And in these multi-electron atoms, the energy depends on both n value as well as l value. So have you noted down this? Shall I move to the next page? Shweta, are you having any network issue?
Sir, I can't hear you properly. I guess it's my network.
Exactly. It is, I think you have a network issue. Can
Yes, sir.
others listen me properly?
Sir, I can.
Okay. So that means Shweta is having some network issue. Okay, shall I move to the next page? Have you noted down this?
Yes.
Okay, so let's then move to the next page. So I told you that in case of multi-electron atoms, for example, if I'm having helium up to Organization, last element of the periodic table. Now, how to tell the order of energy? So there is a rule that is known as Bohr-Bori's rule. Bohr-Bori's rule. Bohr-Bori's rule. Now, what this rule states, it is actually also known as N plus L rule. As I told you that the value of energy, it depends on N as well as L value. So according to Bohr-Bori's rule, or what we can also call it as N plus L rule, it says that smaller the N plus L value, smaller the N plus L value, lesser will be the energy. Got it? Lesser will be the energy. So that means if N plus L value is small, then the energy will be also less. This is very important. So if N plus L value is very high, then energy will also be high. Next, what you have to remember that now if N plus L comes out to be same, then what you will do? If the value of N plus L comes out to be same, then smaller the N value, lesser will be the energy. Got it? So this is what you have to remember in this Bohr-Bori's rule. So simply what you will do, you will just calculate N plus L value. If N plus L value is small, then it will have lesser energy. And if N plus L value is very high, then energy will also be high. But if for two orbitals, N plus L value comes out to be same, at that time you have to check N value. Smaller the N value, lesser will be the energy. So let's give the examples. For example, if I'm just talking of, let's say 1s and 2s. So I have to tell that which has higher energy and which has lower energy. So first we will calculate N plus L value. So here N value is 1. And what is the L value? For S, I have told you that the L value is 0. So N plus L, what is N plus L here? N plus L is 1 plus 0. So that is your 1, right? Now, in case of 2s, you can see here that N value is 2 and L value is also here 0. So N plus L, what will be that? That will be 2 plus 0. So that will be equal to 2. So here N plus L, it is 1. That means it's small. So its energy will be also less. So 2s will have higher energy because N plus L is here 2. Got it? Okay, then if I will just write, let's say 3s. Okay, let me write 2p. First, let me write here 2p. So can you tell me what will be the energy of 2p as compared to 2s? Will it be higher or lower? So in case of 2p, you can easily check it out that N value is 2. And here L value is 1 because for p, L value is 1. So N plus L, that is here 2 plus 1. So that is equal to 3. So as 3 is bigger than 2, so that means its energy will be high. So first it will be 1s, then it will be 2s, then the energy of 2p. That means 2p will have higher energy than 2s. Similarly, 2s will have higher energy than 1s. Got it? This is known as Bohr-Bori's rule, or what we also call it as N plus L rule. Is it clear now?
Yes, sir.
Okay, then tell me if I will now write 3s. So in case of 3s, what is N value? N value is 3.
3.
What is L value? L value is 0,
0.
because for S, L is 0. Okay, what is N plus L here? That is 3 plus 0, that is 3. Now here it is also 3. In case of 2p, it was also here 3. And in case of 3s, it is also 3. So what we have to do? When value of N plus L comes out to be same, so what we have to do? we have to check out n value. So smaller the n value, lesser will be the energy. So 2p, here n value is 2, so its energy will be less as compared to 3s. So you have to remember that first it will be 1s, its energy will be very least, then it will be 2s, then it will be 2p, then it will be 3s, right? And then it will be 3p, etc. You can now calculate easily the order of energy. So can you? I hope that you can calculate. So any doubt here? Have you noted down this? Shall I move to the next page?
Yes, sir.
So, okay, so then if I will write, let's say I'm writing here 4s and 4p, and I'm also writing here 3d. So you had to tell me the order of energy. So what will be here, n plus l? So if you just calculate n plus l, so that will be here 4 plus 0, so that's 4. And here it will be 4 plus 1, that is 5. Here it will be 3 plus 2, that is 5. So definitely 4s, its energy will be small, less as compared to 4p. But now in case of 4p and 3d, n plus l comes out to be same, right? What to do now? Whenever n plus l comes out to be same, we have to check the n value. Smaller the n value, lesser will be the energy. So that means 3d will have lesser energy than 4p, or you can say that 4p has higher energy than 3d. Or you can also write it like this, that is, first it will be 4s, then it will be 3d, and then it will be 4p. Got it? This is the order of energy. So is it now clear? Then we have to write the electronic configuration. So first of all, let's define what is electronic configuration. So can you tell me what is electronic configuration? How to define this? What is electronic configuration? It simply means filling up of electrons in various shells, subshells, or orbitals. So I'll write it here. So electronic configuration means filling up of electrons in various filling up of electrons in various shells, similarly subshells, and orbitals. So that's called the electronic configuration. But in order to write the electronic configuration, that means in order to fill the electrons in various shells, subshells, and orbitals, we are actually having some rules to follow. So the first rule is known as Abou's principle. Abou's principle. This will be very important. Abou's principle. So can anybody tell me who is this Abou? Can anybody tell me who is this Abou here? Is it the name of a scientist? Can anybody tell me, is this Abou name of a scientist or not? Abou is not the name of any scientist. Abou is a German word. So you have to remember this, that Abou is a German word which means building up, which means building up. So this is very important to remember, that Abou is a German word which means building up. And now what this principle actually states, it states that electrons are filled in orbitals in increasing order of energy. So I'll write it here, that electrons are filled in orbitals. Electrons are filled in orbitals in increasing order of energy. In increasing order of energy. So this is what actually Bauer's principle states. So it states that whenever we have to fill the electrons in various orbitals, what we have to do? We have to follow the increasing order. That means first you will give electrons to that orbital whose energy is very low, and then we will move towards the next orbital. That means first we will give electron to that orbital whose energy is very small, and then we will give electrons to that orbital whose energy is higher, and then we will move similarly in the increasing order of energy. So this is the building up. Whenever we have to actually make any building, what we do? We first make the bed, the base of the building, and then we move towards the roof. So Sam is here that according to Abau's principle, whenever electrons are filled in orbitals, we have to fill them in increasing order of energy. So is it now clear? Shall I move to the next page?
Yes, sir.
Okay. So now how to remember this increasing order of energy? I have told you that we can tell the order of energy from N plus L rule, right? N plus L rule. That's also known as Bohr-Buri's rule, right? But sometimes you can also remember this from a diagram that is known as Mohr's diagram. So if you are not using this N plus L rule, still you can tell that which orbital has higher energy and which has lower. So for example, first tell me that if I'm having the first shell, that's your K shell. So in case of K shell, I'm having only one subshell, that's 1s, right? We have already discussed this in the quantum numbers, 1s. Now, in case of L shell, I'm having two subshells. One is your 2s, another is your 2p, correct? And then in case of M shell, I'm having 3s, 3p, and 3d. And then in case of N shell, I'm having 4s, 4p, then it is the 4d, and then it is the 4f. Similarly, in case of O shell, the subshells will be 5s, and then it will be 5p, then it will be 5d, then it will be 5f. Similarly, in case of P shell, it will be your 6s, then it will be 6p, and then it will be 6d. If I will write the Q1, it will be your 7s and 7p. Now there are some few questions for you. Can you tell me that what I have written here, 1s, why not 1p? Does 1p exist?
No, sir.
Exactly.
Only
1p doesn't.
S subshell is there in first shell.
Exactly. In case of first shell, there is only one subshell, that is 1s. So 1p doesn't exist. 1p does not exist. And now can you here tell me that I have written here 4s, 4p, 4d, 4f. Similarly, 5s, 5p, 5d, 5f. But there is also 5g. But why I have not written it here? Can anybody tell me why? Why I have not written here the 5g?
Sir,
You can check the text.
maximum is only till F.
See, actually 5g is there, but actually we are only having 118 elements. So there isn't any need of 5g because we are having only 118 elements. So that means we have to only distribute 118 electrons. So that's why there is no need of 5g. Similarly, 6f is also there. 6g is also there, but we don't have any need of these because we are only having 118 electrons. So that's why I'm not writing these in this diagram. And then similarly 7s, there is also 7p, 7d, 7f, 7g, 7h, etc. But we do not require those. So now see how to remember the order of energy. So first you will just draw the diagonal lines here like this. 1s, and then you will just draw 2s. You have to just connect to these and diagonal lines here. Then you can tell the increasing order of energy. So that means first it will be your 1s, which will have a very low energy. So first you will just complete these diagonal lines, just as I am showing here, you will just note down it. So it's your 4p, 4f, 5d, 6p, and then 7s. Then it is your 5f, 6d, 7p. Now tell me here, what you have to do next. Next is that you just go from this 1s. So first energy will be very low for 1s, then the next will be 2s. So how do you have to move? This is 1s, then you will just go again like this, and then you will just come back. So it is 2s. After 2s, it is not the 3s, it is then 2p. So you have to move again back and then come again. So after 2s, the energy of 2p will be higher, and then after 2s, it will be your 3s. 2p, after 2p, it will be your 3s. After 3s, you have to again move here just like this. So after 3s, it will be your 3p. Got it? After 3p, it will be your 4s. Correct? Now, can you tell me what will be the next orbital having higher energy after 4s? So after 4s, it will be your 3d. Got it? This is the increasing order of energy. And what will be after 3d? After 3d, it will be your 4p, right? After 4p, it will be your 5s. And after 5s, what will be the next? You have to again move back and then just come again. So after 5s, it will be your 4d. After 4d, what will be the next? Next will be after 4d, it is your 5p, then it is your 6s. So 5p, then it will be your 6s, correct? After 6s, what will be the next? I hope that you have understood this now. So this diagram is very important because you can directly tell that which orbital is having lesser energy and which is having higher energy. So after 6s, it will be your 4f. After 4f, it will be your 5d, correct? After 5d, it will be your 6p, and then it will be your 7s. Then it will be your 5f. So etc. So I hope that now you can tell the increasing order of energy from this diagram. This diagram is known as Moller's diagram. So have you noted down this? And if you also calculate this order of energy from this N plus L rule, it will also come out to be same. N plus L rule, or what we also call it as Bohr-Boris rule, it is same. The order of energy, it will be same, whether you are just calculating from Bohr-Boris rule or whether you are just saying it from this diagram. So this diagram is very important and it is easy to draw and it is easy to tell which orbital will have lower energy and which orbital will have higher energy. So this is according to the Abou's principle. That means according to Abou's principle, we have to fill the electrons in various orbitals in increasing order of energy. So that means first you will give electrons to this 1s, and then we will just move towards the 2s, and then if 2s gets fully filled, then we will move towards the 2p. If it also gets fully filled, then we will move towards the 3s orbital. Got it? Shall I move to the next page?
Yes, sir.
Okay, then you can now easily write the electronic configuration. So let's start with the hydrogen. So hydrogen, its atomic number is 1. So what will be the electronic configuration? It will be 1s1, right? Because there is only one electron and it is to be filled in that orbital whose energy is very low. So energy is very low for 1s. Then I'm having helium, atomic number 2. So the electronic configuration will be 1s2. That means there are 2 electrons and they will just go in this s subshell, because s subshell can have maximum 2 electrons. And then it is your lithium, atomic number 3. So it has 3 electrons. So first you will write 1s2, because s can only accommodate 2 electrons. Then it is your 1s2, then it is your 2s1. After 1s, the energy of 2s, it is higher, as we have seen from the previous diagram, or you can also calculate it from n plus L rule, that is the Bohr-Boris rule. But better is to draw this diagram. It is easy to draw and it is easy to tell the increasing order of energy from this Molar's diagram. Got it? So can you tell me what will be the electronic configuration for next element, that is the beryllium, atomic number 4? I hope now you can easily write the electronic configuration. So that's 1s2, then it will be 2s2, because after 1s it is 2s. So there are 4 electrons. So first 2 electrons you will go to this 1s, and then the next 2 electrons in this 2s. So after beryllium there is boron, atomic number 5. So it is your 1s2, 2s2, and then now 2s is also fully filled. It will, next electron will go into 2p. So it will be 1s2, 2s2, 2p1. P can have maximum 6 electrons. This is very important. For example, if I write the carbon, atomic number 6, so what will be the electronic configuration? It will be 1s2, 2s2, and then it will be 2p2. Similarly, in case of nitrogen having atomic number 7, it will be your 1s2, and then it will be your 2s2, then it will be your 2p3. Got it? Because P can have maximum 6 electrons. I hope you remember we have already calculated the number of electrons that can be accommodated in a particular shell. I told you that S can accommodate maximum 2 electrons, and P can accommodate maximum 6 electrons, D can accommodate maximum 10 electrons, and F can accommodate maximum of 14 electrons. Got it? So what will be the electronic configuration for this oxygen? Atomic number 8. So it will be 1s2, then it will be 2s2, and then it will be 2p4. So 2 and 2, 4, 4 and 4, 8. So then if I will just write the fluorine, atomic number 9, so it will be your 1s2, 2s2, 2p5, 2 to 4 and 5, 9 exactly. So if I have to write the electronic configuration of neon, atomic number 10, so it will be your 1s2, 2s2, and then it will be your 2p6. Got it? Because P can have maximum 6 electrons. So have you noted down this? Shall I move to the next page? Have you noted down? Shall I move to the next page?
Yes, sir.
Okay, so now there is another principle. So that's actually known as Hund's rule. That's actually known as Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Now, what this rule actually states? It states that in case of degenerate orbitals, so what are degenerate orbitals? Degenerate are those orbitals which have same energy. So I will write it here that in case of degenerate orbitals, in case of degenerate orbitals, electrons are first filled singly. Electrons are first fill it singly. And then pairing takes place. And then pairing takes place if more electrons are available. If more electrons are available, right? So this is what actually Hund's rule states. So you have to remember that in case of degenerate orbitals, now what are degenerate orbitals? I told you that degenerate orbitals are those which have same energy, correct? Degenerate orbitals have some energy. Degenerate orbitals have some energy. So if I just give you the example, for example, if I will write 2px, I will write the 2py and 2pz. So can you tell me what is their increasing order of energy? So actually all these three have same energy. They have equal energy. They are your degenerate orbitals. So can you tell me why? Because if you just calculate n plus L value, what is n value here? In all these, n value is 2. And what is L value? This is your P, this is also P, this is also P. So all have L value 1. So 2 plus 1, that is 3. So n plus L, it is 3 for all. N plus L is here 3, and here it's also 3, and here it's also 3. So that means now I have told you that if n plus L comes out to be same, then what we have to do? We have to check the n value. But if you just check it out here, n value is here 2, it's again here 2, it's again here 2. So that means n value is here same. So when n value is same, so that means their energy is also same. So such orbitals are known as degenerate orbitals. So degenerate orbitals are simply those which have same energy. Got it? Have you noted down this? Shall I move to the next page? Have you completed now? Shall I move to the next page?
Yes, sir.
Okay. Now we have seen that according to the Hund's rule, whenever we have degenerate orbitals, for example, if I'm having, let's say, the 3p orbitals, they are degenerate. That means px, py, and pz, they are your degenerate orbitals. Px, py, and pz, they are degenerate. They have same energy. So if let's say I'm having one electron, so I will just give it to this px with up spin. Now, if I'm having one more electron, let's say I'm having 2 electrons. So at that time, what I will do, I will just give one more electron to this py. And now if I'm having one more electron, then I will just give this electron to this pz. So first electrons are filled singly. This is very important. First electrons are filled singly. That means pairing doesn't take place. That means you will not just give the 2 electrons in this px. For example, if I will write like this, if I'm having the 3 electrons, and if I'm just distributing, if I'm just filling these 3 electrons like this, let's say 2 electrons in this and 1 in this. So is it correct? No, this will be incorrect, because according to the Hund's rule, we have to first give 1 electron to each degenerate orbital, because all these 3 have same energy. They are your degenerate orbitals. So first you will give 1 electron to each orbital. Got it? Is it now clear? For example, if you have to tell me that whether it is correct or incorrect, let's say I'm having one electron and that is just like this. Is it correct or incorrect? According to the Hund's rule, it is also incorrect, because first you will just give electron to this px, then we will move to the py and pz. So similarly, if I'm just writing the electronic configuration like this, so tell me, is it correct or incorrect? It is also incorrect, because according to the Hund's rule, first you have to give one electron to each of the orbital. Pairing will not take place unless each orbital is singly filled. That means we have to give first of all one electron to each orbital. Got it? Is it now clear? So for example, let's say I'm having 4 electrons and I have to distribute these in, let's say, px, py, and pz. So how I will distribute? So let's say this is your px, py, and pz. So first I will give one electron to each, 1, 2, and 3. Now, since I am having one more electron, there are total 4 electrons. So that means now pairing will take place. So now I will give one more electron to this px. So let's say this is your 2px. Let's say this is your 2py. And let's say it's your 2pz. So you have to remember that first you have to give one electron to each orbital, and then pairing will take place. Then you can just give 2 electrons if we have first given one electron to each degenerate orbital, because these 3 are degenerate orbitals. Similarly, if I'm having, let's say, d subshell, in case of d subshell, I hope you remember that there are 5d orbitals, right? So let's say this is my dxy, this is dyz, dzx, dx square dash y square, and dz square. So can you tell me, if I'm having 3 electrons, how I will distribute? If I'm having only 3 electrons, how I will fill these 3 electrons in these 5d orbitals according to the Hund's rule? According to Hund's rule, you will first give one electron to each orbital. So 1, 2, and 3. So as I was having only 3 electrons, so this is the correct way to represent this. Got it? So this is Hund's rule. So you have to remember these 3 rules. One is the Abou's principle, another is the Hund's rule, and the third one is the Pauli's exclusion principle, which we have already discussed it in the yesterday class, right? Pauli's exclusion principle, we have studied it yesterday. According to Pauli's, I told you that an orbital can accommodate maximum of 2 electrons with opposite spin, right? Okay, so have you noted down this? Shall I move to the next page? So shall I move to the next page? Have you noted down this? Shall I move to the next page?
Yes, sir.
Okay, so now I hope you can now write the electronic configuration. For example, if it is your hydrogen, atomic number 1. So if I will just write it, and that is 1s1, the electronic configuration was 1s1. So how you can write it diagrammatically? So if I represent 1s orbital like this, so this box, it represents your 1s orbital. So you will just show here the electron with this up spin. So there is only one electron. Now, if I just talk of helium, helium has atomic number 2. So its electronic configuration is 1s2. So how you can show it diagrammatically? So S has 2 electrons. So it is just like this, 1 and 2. So then I'm having the lithium, atomic number 3. So it will be your 1s2, and then it will be your 2s1. So diagrammatically, how you can show it? 1s2, that means there are 2 electrons. So you can just show one up spin, another down spin. Because according to the Pauli's exclusion principle, I have told you that an orbital can accommodate maximum of 2 electrons with opposite spin. And then 2s1, so that means there is only 1 electron, so that's up spin. Similarly, for beryllium, atomic number 4, so how you will write? That is 1s2, then it's your 2s2. So that means 1s2, it is just like this. There are 2 electrons here, and then it is your 2s2, so there are also 2 electrons. Got it? So then it is your boron, atomic number 5. So its electronic configuration is 1s2, then 2s2, and then it is 2p1. So here, what you will do, 1s2, so you will just write the 2 electrons like this, one up spin, another down, and then 2s2, again you will show it here, one up spin, another down, and then we are having here 2p1. So in case of 2p1, I told you that in case of p subshell, there are 3p orbitals, right? So one will be your 2px, another will be your 2py, and another will be your 2pz. So there is only one electron, so you will just give it to this 2px with up spin. So this is the correct way to represent the electronic configuration of this boron according to the Hund's rule. So just we're having the carbon. Carbon is having 1s2, there are 6 electrons, 2s2, and then it will be 2p2. But diagrammatically, you can show it like this. That's 1s2, there are 2 electrons, one up spin, another down. Here also it is your 2s2, and then it is your 2p2. So in case of 2p, you are having actually 3p orbitals, right? So electrons are only 2, so you have first to give 1 electron to each orbital, that is 2px1 and 2py1. 2px1 and 2py1. Similarly, in case of nitrogen, atomic number 7, what is the electronic configuration? It is 1s2, then it's your 2s2, and then it's your 2p3. So diagrammatically, you can show it like this. 1s2, there are 2 electrons. Then it's your 2s2, there are also the 2 electrons. But in case of 2p, we are having the 3 electrons. And we know that these 3p and that these p orbitals, they are actually 3, px, py, and pz. And according to the Hund's rule, we are having the 3 electrons. So first you have to give 1 electron to each orbital. Got it? With up spin. So this is correct way to represent the electronic configuration of nitrogen. So have you got it? Any doubt here? So have you noted down this? Shall I move to the next page?
Yes, sir.
Okay. So this is for nitrogen. I hope that now you can yourself write the electronic configuration for oxygen, right? So oxygen, it has atomic number 8. So it is your 1s2, and then it is your 2s2, and then it's your 2p4. So here you can see that first it's 1s2. So that means there are 2 electrons in this 1s, and then it is your 2s. So it has also the 2 electrons, and then it is your 2p. So in case of 2p, we're having 4 electrons. So first what we will do, according to the Hund's rule, first you will give one electron to each because they are having equal energy. And then pairing will take place. So then you will give one more electron to this 2px. Got it? So this is very important. And I hope that you can write the electronic configuration of all these elements. Now there is actually exception. Some elements show the exceptional electronic configuration. That is, one is your chromium, and another is copper. Chromium and copper show exceptional electronic configuration. They show exceptional electronic configuration. So let's see the electronic configuration of chromium and copper. So first I will write here the chromium. So chromium is having atomic number 24, right? So its electronic configuration, it should be 1s2, 2s2, then it is your 2p6, and then it is your 3s2. Increasing the order of energy we had follow. Then it's your 3p6, then it is your 4s2, and then it is your 3d4, because we are having 2 and 2 4 and 6 10 12 18 20 and 24, correct? But this is not correct. This is incorrect because it actually shows the exceptional electronic configuration. So what is that? It's exceptional is like this, that is 1s2, 2s2, and then it is your 2p6, then it is your 3s2, 3p6, and then it will be 4s1. There is one electron from this 4s, it actually jumps, it excites to this 3d, so it becomes 4s1 and 3d5. So this is the correct, and this is actually the exception shown by this chromium. So chromium and copper, they will be important and they are asked in the exam, so you have to note down this chromium and copper. So I will give you the reason that why they show the exceptional electronic configuration, but first you will write down this. So have you noted down this?
Yes, sir.
Okay, then Sam will be the for copper. So for copper, copper has atomic number 29. So it has 29 electrons and we have to distribute these. So it will be 1s2, 2s2, then it will be your 2p6, and then it will be your 3s2, and then it will be your 3p6, then it will be your 4s2, and then it will be your 3d10. It should be like this, but this is incorrect. It shows the exception. So what is the exception? Exception lies only in the last one, that is, it will be here Sam, 1s2, 2s2, 2p6, then it will be 3s2, then it will be 3p6. Now here is the difference, that 4s1, that means one electron from this 4s, it actually jumps. Oh, sorry, it will be here 3d9. How many electrons are there in case of copper? Can you count? Can you count number of electrons in copper? There are 29. So 2 and 2, 4, 4 and 6, 10, 12, 18, 20, and 29. So now when one electron from this 4s, it jumps into this 3d. So it will become 3d10. Got it? This is actual and this is the correct one. This is the exceptional. So that means you have to remember it is not here 3d4, but it is 3d5 in case of chromium. And in case of copper, it is not 3d9, it is 3d10. So have you noted down this? This is very important. Chromium and copper, they show exceptional electronic configuration. So shall I move to the next page? Have you noted down this?
Yes, sir.
Okay. So now why this chromium and copper, they show the exceptional electronic configuration? So first of all, let me write here the reason that why they show the exceptional electronic configuration. There are two reasons actually. One reason is that is the symmetry. Do you know that symmetry leads towards stability? So I will write it here. A reason. There are two reasons. One is the symmetry. Symmetry always leads towards stability. You have to remember this, that symmetry always leads towards stability. Okay, I will write it here. That symmetry always leads towards stability. So that means anything which has symmetry in it, so that will be more stable. Symmetry always leads towards stability. Now, can you tell me if you are having 3d4, that means there are only 4 electrons, right? So how you will distribute according to the Hund's rule? We know that according to the Hund's rule, we have to first give one electron to each. So that means you will give 1 electron to this 3d, and then 1 to this, again here 1 and 1. So there are 4 electrons in this 3d. And now this was the incorrect one, right? In case of chromium, I told you that it is actually 3d5, right? Now, if I will just write the 3d5, so what will be the electronic configuration? Diagrammatically, how you can show it according to the Hund's rule? According to the Hund's rule, what you have to do? You have to give one electron first. Each orbital is singly filled, so you will just write 1 electron here, 2, 3, 4 and 5. Now you can easily check it out that which is more symmetrical. Is it 3d4 or 3d5? So definitely it is your 3d5. 3d5 is more symmetrical because each orbital is having one electron. But here in case of 3d4, one orbital is empty. So that means you are right that 3d5 is symmetrical. 3d5 is symmetrical than 3d4. Got it? 3d5 is symmetrical. It is more symmetrical than 3d4. Got it? Similarly, can you tell me, will in case of copper, we are having 3d9, and this is actually the incorrect one, and the actual is 3d10. So which is more symmetrical? Will it be 3d9 or will it be 3d10? So can you guess? Will 3d9 be more symmetrical or 3d10?
3d10.
Exactly, 3d10 will be more symmetrical because we have to actually follow the Hund's rule. So according to Hund's rule, first you have to give 1 electron to each, and then actually pairing takes place. So if I will just write 1 electron here, and then pairing takes place, so that means there will be now one orbital will be having only 1 electron, and others will be having two electrons. So this last electron orbital, it has only 1 electron, so that means it is not symmetrical. But if you just check out this one, that is your 3d10, so here you can see that each orbital is having two electrons in it, so this will be more symmetrical. And I told you that symmetry always leads towards stability, so you will write that 3d10 is more symmetrical, or you can say it is more stable than 3d9. Got it? Is more symmetrical than 3d9. So this is one of the reason, that is the symmetry. But there is also another reason. So first tell me, have you noted down this? Shall I move to the next page? If you will just increase the speed of your notebook, then we will complete this chapter today. We have to complete this chapter today. We are going to complete it. So a little bit you have to be fast. So have you noted down this? Shall I move to the next page?
1 second, sir.
Okay, sure.
Done, sir.
Okay, great. So let's now see another reason. Another reason is the exchange energy. So can you tell me what is actually the exchange energy? See, exchange energy is actually the amount of energy which is released when an electron, okay, I will write it here. Exchange energy is the amount of energy released when an electron exchanges its position, exchanges its position in degenerate orbitals. I told you that what are degenerate orbitals? Degenerate orbitals are simply those which have same energy. In chemistry, we call degenerate orbitals to those which have same energy, right? Okay. Now, when actually, for example, let's say I'm here having, let's say I'm having these three p orbitals. So you tell me that these p orbitals, they have same energy. So this is your px, then it is your py, and this is the pz. Now tell me here that if electron exchanges its position, for example, let's say this electron moves to this orbital and this one electron moves to this one. So what is happening? The electrons are just changing their position, they are exchanging their position. But when they will just exchange their position, energy is released. And that amount of energy released, that's called the exchange energy. Got it? That's called the exchange energy. So now can you tell me that if more the number of exchanges, more will be the energy released and more will be the stability. So I will write it here that more the number of exchanges, more the number of exchanges, more will be the, more the number of exchanges, more will be the exchange energy, right? And when more is the exchange energy, more will be the stability. Hence, more will be the stability. Hence, more will be the stability. More will be the stability. So this is to be noted down here that if exchange energy is very high, then stability will also be more. So more the number of exchanges, more will be the exchange energy, and hence more will be the stability. Now, can you compare in case of chromium? In case of chromium, if it was your D4, right? D4. So in case of D4, how many electrons you are having? You are having just the 4 electrons like this, 1, 2, 3, 4, and 5. So this is your 1 electron here. This is the second, third, and this is the fourth one. Now, can you tell me if I just talk of this first electron? So this first electron, it can exchange with this second electron. It can also exchange with this third electron. It can also exchange its position with this 4. So 1, 2, 3 exchanges are here, isn't it? 3 exchanges. Now, if I just talk of the second one electron, so which is the second one electron? Second electron is like this, 1, 2, 3, 4, and 5. So this was the first electron, this is the second, third, and fourth. So if I just talk of this one electron, that is your second electron, it can exchange with this electron. And it can also exchange its position with this electron, right? So there are 2 exchanges are possible. I'm just showing the forward exchanges. I hope you are understanding this. And then the next one is am I audible?
Yes,
Yes, sir.
Okay, then the next electron is we are having like this 1, 2, 3, 4. 1, 2, 3, and 4. So this is the third electron now. So this third electron, it will show only the one exchange, that is with this electron, fourth electron. So how many total exchanges are there? If you can count 3 and 2, 5, and 1, 6 exchanges, right? Got it? So this is your D4, but I told you that chromium shows exceptional one, that is your D5. So can you count the number of exchanges in case of D5? I hope you can draw these diagrams, and then you can also count the number of exchanges here. So in case of D5, you are having 5 electrons in these d orbitals. So 1, 2, 3, 4, and 5. So you can now check it out that here if I'm just talking of the first electron, so how many exchanges it will show? 1, 2, 3, and 4. So the electron which is present in this first orbital, it can show 4 exchanges, right? Are you getting this? I hope you are getting this. So it will show 4 exchanges. Then if I will just show the next one. So what is the next one? Next is the second electron. So how many exchanges it will show? If I'm just talking of the, let's see, 1, 2, 3, 4, and 5. So we are having here the 5 electrons, 1, 2, 3, 4, and 5. So if I'm just talking of the exchange, the second electron, it will just show exchange like this: 1, 2, and the 3. So this will show 3 exchanges here. And then if I'm just talking of the third electron, how many exchanges that will show? Third one electron. 1, 2, 3, 4, and 5. So we are having the 5 electrons here: 1, 2, 3, 4, and 5. So now I'm just talking of which electron? The third one. So third one, it will show only 2 exchanges. So one is this fourth electron with the fourth electron, another is with this fifth electron, 2 exchanges. Now if I'm just talking of the fourth electron, so that will only show the 1 exchange, right? So then can you count the total number of exchanges here in case of D5? Can you count the total number of exchanges? So you can check it out that this will show only 1 exchange, the fourth electron. So how many total we are having? If you just count 4 and 3, 7, 8, 9, and 10. So there are 10 exchanges. Now what I told you that more the number of exchanges, more will be the exchange energy, and hence more will be the stability. So if in case of D5, the number of exchanges is 10, so that means exchange energy will be more. And when exchange energy is more, so that means stability will be also more. So that is why chromium shows exceptional electronic configuration, and copper also shows the exceptional electronic configuration. So have you noted down this? Is it now clear? Any doubt here?
No, sir.
Okay, then let's move ahead. Next, you have to remember here that is actually noble gas electronic configuration. So I will write it here. I hope you will just write it: noble gas electronic configuration. Noble gas electronic configuration, or it's also known as inert gas electronic configuration. Inert gas electronic configuration. So what is this noble gas? Noble gas actually here means when you just write the electronic configuration in terms of noble gas. For example, if I just write here the lithium, atomic number 3. So can you tell me which noble gas comes before this lithium? It is definitely the helium. Helium is the noble gas. Helium, its atomic number is 2. So then you will just write, so it was your 1s2, 2s2, 2s1. So you will just write 2s1, because in place of 1s2, you have just written down here the noble gas. So what was the lithium? Lithium was actually, it was having electronic configuration 1s2, and then it was 2s1, right? But helium, in place of this 1s2, we have just written down here the noble gas helium. So this is known as noble gas electronic configuration. For example, if I will write the sodium, its atomic number is 11. So what was the electronic configuration? It was 1s2, 2s2, and then it was your 2p6, and then it was your 3s1. So if I just write in terms of noble gas, before sodium, we are having the noble gas neon. Neon is having atomic number 10. So it is just written in this square bracket. So 10, so that means 2, 2, 4, and 6, 10. So then I will just write 3s1. So that means this noble gas electronic configuration, it is the short way to write the electronic configuration, and it's easy also. For example, if you just write the potassium atomic number is 19. So what was the electronic configuration? Its electronic configuration is 1s2, 2s2, and then it's 2p6. Then it's your 3s2, isn't it? Then it will be your 3p6, and then it will be your 4s1. So now in terms of noble gas, how you will write it? So potassium, before this, we are having the noble gas argon. So you will write argon 18, and then you will write, so we are having 2, 2, 4, 6, 10, 12, 18. So up to this, you have just written, in place of this, you have written the noble gas argon. And after that, you will just write the 4s1. So it is now very easy. It is the short way to write the electronic configuration. And this is known as noble gas electronic configuration, or it's also known as inert gas electronic configuration. So have you noted down this? So I hope that you can write the noble gas electronic configuration. For example, if I'm just talking of carbon, its atomic number is 6. So it's 1s2, 2s2, 2p2, right? Now, if I'm just writing in terms of noble gas, how I will write? So which noble gas is coming before this carbon? It is definitely the helium, because neon is having atomic number 10. So that's after carbon, but you have to write that noble gas which is before this carbon. So you will just write helium 2, and then you will write 2s2, 2p2. Got it? Helium 2, 2s2, 2p2. This is the noble gas electronic configuration of this carbon. Got it? Any doubt here? So have you noted down this? Shall I move to the next page? Shall I move to the next page?
Yes, sir.
Yes, sir.
Okay. Okay, then it is the last point which you have to note down. Then we will just conclude this. So that is the electronic configuration of ions. I hope you can also give the electronic configuration to the ions. We are having two types of ions, that is the cation and the anion. For example, what was the electronic configuration of lithium? Atomic number 3. It was 1s2, 2s1, right? Is it right? But if I will write Li positive, so positive means it has actually lost one electron. So that means its electronic configuration will be 1s2, because it has actually lost one electron from this 2p. Electron is always lost from the outermost shell. Got it? So it will be 1s2, or you can also write 2s0, or if you don't write this, that's also correct. Similarly, if I just write the sodium, what was the electronic configuration of sodium? It was 1s2, and then it was your 2s2, right? Then it was your 2p6, and then it was your 3s1. Now, if I had to write the electronic configuration of any positive, how I will write? So positive means what? Positive means it has just lost one electron. So when it loses one electron, it will just lose it from the valence shell, from the outermost shell. So it will be now 1s2, 2s2, 2p6, because this is the outermost shell, that is 3s. So it has just lost one electron from this 3s. Got it? I hope that it's clear. It's very easy. For example, if you just write the electronic configuration of this fluorine, it will be your 1s2, 2s2, and then it will be your 2p5. But if I'm just writing, let's say F negative, that is your fluoride ion. Now, negative charge means it has actually gained one electron. So I will write 1s2, I will write then 2s2, and then I will write it 2p6, because it has just gained one electron. So that means that will go into this 2p, because p can have maximum 6 electrons. Got it? So is it now clear? For example, if I will write hydrogen, its atomic number is 1. So its electronic configuration is 1s1. Now, if I'm writing H negative, negative means it has just gained one electron. So it will now be 1s2. Correct? So with this, I hope that you have got this, how to write the electronic configuration for ions. And with this, we have just completed this chapter, that is the atomic structure or the structure of atom. So if you are having any doubt, any question, you can let me know. So is anybody having any doubt, any question?
Yes, sir.
So then let's stop today's topic here. And we have completed this chapter. I hope that you will go through this unit. You will just revise each and everything and you will then face the exam, right? Wish you all the very best. Have a nice day ahead.
Thank you, sir.
Most welcome.
Thank you, sir.
Most welcome. Bye.